The Lunar Lander was a mission developed by the European Space Agency's Human Spaceflight and Operations Directorate with the aim of demonstrating Europe's capability to safely deliver payloads to the surface of the Moon. The primary objective of the mission was to showcase the technologies required for achieving a soft and precise landing while autonomously avoiding surface hazards that can endanger landing and surface mission safety. These technologies are expected to be an asset for future human and robotic exploration missions. Unfortunately, the project was put on hold during the 2012 ESA Ministerial Council. The mission scenario of the Lunar Lander began with its launch from Center Spatial Guyanais, Kourou in late 2018 on a Soyuz launcher. The lander was injected into a highly elliptical orbit, HEO, by a Fregat-MT upper stage through a series of intermediate orbits. After the Fregat separation, the lander used its own propulsion to enter the final lunar transfer orbit. Following several weeks of overall transfer time, the lander injected itself into a polar orbit around the Moon. After a series of apollyon and parallel lowering maneuvers, the lander reached its final low lunar orbit, LLO, at an altitude of 100 kilometers. Once the Lunar Lander reached the low lunar orbit, it prepared for the final phase of the mission by waiting for the correct constellation of orbit, Earth and Sun geometry. The lander also performed the checkout and calibration operations of the systems critical for landing. The time spent by the lander in LLO before the start of the landing operations was expected to last from a number of weeks up to a maximum of 3 months. The descent and landing phase of the mission began when the lander performed a deorbit burn close to the lunar North Pole. This burn decreased the orbit's parallel to about 15 kilometers, some 500 kilometers ahead of the lunar South Pole, half an orbit later. During the coasting period, automatic visual recognition of landmarks on the lunar surface was used to determine the lander's precise location and ensure correct positioning at the beginning of the final descent. Heading towards the South Pole, the lander entered the final powered descent phase. Using its cluster of thrusters, the lander decelerated and descended. During this phase, varying thrust needs to be applied as the lander approached its landing site. Finer thrust levels were achieved using the ATV engines and pulse modulation. At an altitude of few kilometers, the Hazard Detection and Avoidance System, HDA, evaluated the primary landing site for surface hazards, such as steep slopes, craters, boulders, shadows, etc. If the primary site was deemed unsafe, the HDA had the opportunity to command retargetings to a secondary landing site. When a safe landing site was found, the lander performed a soft touchdown using its legs. Once landed on the surface, the lander carried out critical operations such as the deployment of its antenna and camera mast, and relays the complete package of data relating to the descent and landing sequence back to Earth. The lander relied on direct line-of-sight communication with Earth as no relay satellite was planned for the mission. This configuration implied periods where no communication with Earth was possible because of Earth moving outside the lander's field of view. Nominal surface operations were then initiated, which included the deployment of specific payloads onto the lunar surface via a robotic arm, the activation of other static monitoring payloads on board the lander, and ultimately the acquisition of surface samples using the robotic arm for analysis by instruments on the lander. The Lunar Lander was designed with a cylindrical main body, with 4 landing legs extending from the sides. The circumference of the main body was covered. Thanks for watching. Like and subscribe for more videos like this.